Hi guys, there are several great videos about tree-sitter out there, but I couldn't find one that covers pretty much everything you need to get started. So I decided to create this video. This is a comprehensive end-to-end manual on how to use tree-sitter to develop, debug, and generate the grammar parser from scratch. Throughout this video, we will be using inference programming language tree-sitter parser, which is available on GitHub. And we will cover the following topics. 1. We will break down grammar.js file and explore key tree-sitter API. 2. I show you exactly how to generate, debug, and test your parser. 3. I show you how to write a syntax highlighter and plug it into Neovim. Also, I will show you how to debug your parser in Neovim directly. Ready? Let's get started. We're going to dive into tree-sitter grammars from the ground up. At the high level, grammars are defined by rules, often thought as functions. For example, you'll see statements in the top level rules, which accumulate several more specific rules similarly to the definitions rules. First, let's understand what rules are in tree-sitter, which is a parser generator. Rules are the functions the tree-sitter engine uses to produce the parser itself. This parser is incredibly fast because it's written in C and uses FFI bindings. This allows the C core to be called from other languages, making it suitable for pretty much any language you want to use to process your grammar and to work with your syntax. Let's start with our first rule, comment. Rules, like any other functions in tree-sitter, are defined by their name, in this case, comment. They can be parameterized, though this one isn't. You'll see a fetch right arrow, which indicates that the logic for matching this rule is handled by the underlying tree-sitter engine, not by JavaScript code you write directly. Instead, it's generated by tree-sitter based on regular expressions and helpful built-in functions. We will go through them one by one, covering most of the available functions. The comment rule is defined by a regular expression that matches any symbol except a new line or carriage return. This ensures our comments are single line. You also notice the token function here. Token tells tree-sitter to treat the matched sequence as a single token at the second level of the syntax tree, similar how parsers typically handle them. Another function we see is sequence. Sequence accepts other rules as parameters and ensures they appear in the specified order. In this example, a comment is defined as starting with a trivial backslash. Let's look at rules that can be underscored or not. Underscored rules don't appear as distinct nodes in the syntax tree. They're often used for internal helper rules that are purely for the grammar structure we'll see in action later. The choice function, as seen with identifier here, acts like a fork in the road. It allows the parser to choose between multiple alternatives, in this case either underscore identifier or a reserved identifier. In the grammar tree, identifier appears as a node, but underscore identifier and reserved identifier do not. This is because they are part of our internal structure and aren't directly relevant during the parsing process or subsequent syntax tree analysis. Identifier content is also a regular expression defining a word consisting of letters and underscores. Importantly, spaces are not allowed here. As already mentioned, choice is a function that allows you to choose between identifier or reserved identifier. Reserved identifier, for instance, is a choice of 3 possible keywords: constructor, proof, or Uzumaki. Now let's move on to type argument list. Notice that we define some tokens right away. These are characters or strings that appear verbatim in the matched SDR. Here the type argument list function is parameterized with a dollar symbol. Like this or self in other languages, it allows us to access other rules within the current context. So type argument list usually consists of underscore types. We'll explore underscore type later. Interestingly, we have angle brackets and SAP1 function. Let's look at what SAP1 function does. It's a helper function defined at the very top of the file. It takes two parameters, a rule and a separator. In Tricitor, rules typically allow this pattern. The separator is the delimiter you want to use, like a comma or semicolon. And SAP1 returns the sequence of the given rule with the separator. We also see the repeat function from the Tricitor library, which effectively repeats the rule it accepts as a parameter. In our case, the rule passed to repeat is a sequence of the separator and the rule itself. This will produce something like rule, comma, rule, etc. Let's get back to our type argument list function. Here the SAP1 function is parameterized with underscore type and the comma symbol. The comma symbol is just a shortcut for a comma. The field function is an important Tricitor function. It's used to tag a syntax node, allowing you to access it by name, like type, during later processing in the syntax tree. The idea is that because underscore type will be eliminated as an anonymous node, the higher level node and its children remain. We want to be able to access this field by its type. I can show you a more precise example of this in different video. The comma symbol simply separates the type argument list definition. It's quite similar and doesn't introduce any new functions. The only difference is that instead of underscore type, it accepts an identifier. We can skip the choice function here for now. Type argument list looks like angle brackets, for example, t, comma, v, etc. You can parameterize your function with several placeholders, whereas type argument list allows you to define and use particular embedded language types as parameters. Now let's move on to generic name. It's a sequence field. The identifiers basically define the base name of the root of the generic name. When we use type argument list to construct a well-defined generic name, in our case, it's a sequence of a field like a qualified left side. Precedence is a function that accepts a precedence parameter which you can see defined at the top of the file. The larger the number, the higher the priority of the precedence. Precedence is used by the parser to sort by weight and prioritize matches for higher weighted rules over less weighted ones. Okay, we don't have new concepts here. As usual, we have choice and other functions we already seen. The optional function indicates that the rule is expressed as a parameter, can either be presented or not necessarily represented in the code. It returns a sequence of characters, so we don't need to access the context here. For special case, such as token immediate, it ignores extras like spaces or comments. It's called immediate because it begins matching right after the first symbol it matched, meaning it won't keep spaces or ignore comments. That's why we define string content literal as it is. After a quote mark, anything including spaces and typically meaningless symbols needs to be taken into account. Then we have many shortcuts for punctuation. We also have different small rules for blocks. For instance, this block rule isn't strictly necessary here. We can define it as a separate small rule if we use this construct elsewhere. So let's do that and define other rules for keywords like assume and unique. Then in our text definition for these rules, we can accordingly replace literals with their names. This makes it easier to change something. You don't need to search everywhere. You can address your change in a particular place. Other rules define various constructs, and as you can see, they're quite extensive. You'll find them on GitHub. I will leave a link in the description. Here we have a binary expression definition. It might look a little different. We can have a number of nested operations. So we define them as an array of arrays or of pairs. Then with the map function, we automatically produce a list of rules for the choice function. As you can see, each pair has a precedence, like a Boolean AND or OR operators. This is important for properly sequencing operations in binary expressions. We then construct binary expressions into expression statements. These are like blocks nested within each other. Precedence dynamic is a different concept. While tree-seeder's precedence system is generally static, sometimes precedence cannot be defined statically. That's why in these situations we use precedence dynamic. This dynamic function will be executed at parser runtime to recognize the proper precedence. We then construct higher-level expressions rules with non-while expression and while expression, putting them together into expression. Types are defined with small rules for type names, and then we define them by the language level types we have. Finally, we combine all statements and definitions into the highest level rules in our grammar. Next, we will cover an important thing, the conflict section. Because modern language grammar tend to be not fully unambiguous, conflicts can arise. Tree-seeder cannot automatically resolve them, which is why we have this section. Each pair in this section indicates that the left side prioritizes over the right side. For example, one rule has a higher priority than another. Now that we are done with this, alright, it was the longest section. We have explored the most tree-seeder API you will need to define your grammar. Now it's time to put it on together and generate a parser and see it in action. Let's move on. If you want to build your grammar, you call the tree-seeder build function. Since I have made some changes, I'll do that and test it now. Let's take a look at the config file. As you can see in the script section, I have some scripts that I use for building, installing, testing, and other convenient shortcuts, so I don't have to type everything all the time. If you want to build, other configurations are pretty standard and available on GitHub. Install command runs npm install to compile native Node.js add-ons essential for the parser C components to work with Node.js. Build command compiles the tree-seeder grammar into a WebAssembly module, enabling browser and broad environment compatibility. Prebuildify creates pre-built binaries using an API for stable Node.js compatibility across versions, and strips reduces binary size. Try command launches the tree-seeder playground in the browser, offering a live interactive environment to type code and immediately see the generated syntax tree for debugging grammar rules. Lint uses ESLint to check Grammar.js for code quality and style, catching potential errors early. Bump version is a shell script that I wrote to automatically update the project version number. My custom scripts are B for quick builds, T for runs the grammar test, BT to build and run in one command, the parser, D for debugging, which parses debug in file and outputs syntax tree. TE is for test example, and H is a command that generates syntax highlighting for my example file and shows me the output. The important thing about writing a grammar is having a substantial corpus of tests. They're located in the test corpus directory. In my case, we're structured them by high-level rules like definitions, directives, etc. Within these files, the content is parsed. A triple equals sign enables the test. Then you have the syntax to be tested, and after another triple hyphen sign, you see the syntax tree that the parser produces and expects to produce, like the left part of an assert statement. Let's change this test to break it and see what happens. In this case, let's drop identifier node and run the test. The result shown that TreeSitter identifies the error with the red colored highlighted missed node. If you bring it back and, for instance, add some node that shouldn't be there, another identifier node, and try to run the test, you'll see that with green color encoding, it says there is a redundant node that shouldn't be presented in the syntax tree. If you run the try command, it automatically downloads the container if you don't have it and run the web-based interface for testing your grammar. It's very convenient for testing and debugging your grammar. As you can see on the left hand side, I write the code and it immediately shows the syntax tree on the right side. If I click on the node, it will highlight the parts of the code that constructed those nodes. If you click on the Show Anonymous Nodes checkbox, you'll see those parts of the tree that are synthetic and don't appear as separate or anonymous nodes. You can also check the log checkbox to output logs into the console. The query section is for specific queries. I won't use it right now. Okay, by this time we have a workable parser which correctly processed our language based on the defined grammar. What is good about TreeSitter that it has a great plugin for Neovim, which we will be using for syntax highlighting. Moreover, TreeSitter plugin allows us to point to the local TreeSitter project, which is very useful and handy, and it means that we can use a Neovim plugin for the whole experience of developing in TreeSitter locally. Syntax highlighting file has a slightly different structure, so I will cover it as well. What if I go and look at the file for syntax highlight in the TreeSitter? How do we implement this? We need to go to the Neovim configuration file, and in the plugins configuration, we need to install the TreeSitter plugin and configure it for our custom language. In the particular config, we add a new entry for our grammar with the file extension and the location of the repository and the parser file on the file system. For all these things to work, we need to add queries to the Neovim configuration for highlighting files written in scheme. The structure of the file is as follows. The definition is on the left side. You can see the token or a node, like for all keyword. And on the right side, after the @ symbol, there is a keyword that will be used to identify the color palette. I will leave a link on my X post where I list all these things. Now let's change something. Let's see, for example, that the unique block is highlighted. So what we want to do is change the highlight with this new syntax. But as you can see, we see an error. If you break something, you need to be able to diagnose how to fix it. You have a command, inspect tree. You can run this command inside the file and it splits your terminal. On the left side, you'll see the interactive syntax tree. You can go through it and it's very helpful for debugging. You can navigate through the syntax and see what's wrong. Now, if you want to explicitly rebuild, for instance, if you go and change something in your grammar and other keywords, as we changed before, you need to reflect this in your plugin. So it will highlight the syntax properly. We need to run an update command after building the distribution. And then it compiles. We restart and see no errors. It works. Don't forget to use the title or description comments in the description down below. And if you change something in your highlights, for instance, let's add a highlight for the type keyword. You don't need to rebuild. You just add it and then it automatically reads the scheme highlight scheme. And as you can see, the type keyword is properly highlighted here. Okay guys, we have covered the complete journey of developing tree-sitter parser, from understanding base tree-sitter API, developing the grammar, testing, debugging it, then generating the exact parser and integrating it to the Neovim for syntax highlighting. I hope you will use it and it will be helpful for your own journey in parsing languages or developing your own languages and parsers. So let me know in the comments what languages you would like to parse with tree-sitter, or maybe it's going to be your own language. Thanks for watching and see ya.